Now that we know how to find the derivative of a given function using limits, let's learn how to draw the graph of the derivative given the graph of the function. We have to keep in mind when we're doing this that we want to graph the slope of the original function. So the first thing we're going to do is find the slopes of the original function. The first thing we notice is that there are 4 different sections of graph with 4 different slopes. The first section is from when x is equal to -5 to when x is equal to -2. We'll call that our first section. The second section is from when x equals -2 to when x equals 0. That'll be our second section. And then from when x equals 0 to x equals +2, that's our third section. And then the last section is when x equals 2 to when x equals 5. That'll be our fourth section. Now let's find the slopes of each of these individual sections of graph. The slope of our first section of graph is a negative slope because it goes down from left to right. And that slope is down 3 to the right 3. So that would be -3 over 3, which equals -1. Now let's do the same thing for our second section. This section of graph has a positive slope of 2 over 2, which is +1. Doing the same thing for section 3 and section 4 of the graph gives us a slope of -1 in section 3 and a slope of 1/3 in section 4. And now we'll graph each of these slopes as heights on the graph of the derivative function. In section 1, which is from when x equals -5 to when x equals -2, the slope is constant at -1. So we'll graph a constant function at a height of -1 from when x equals -5 to x equals -2, like this. In the second section of graph, the slope is constant at +1, and that's from when x equals -2 to when x equals 0. So on the graph of our derivative function, we'll graph a height of 1 from when x equals -2 to when x equals 0, like this. And then we'll do the same thing for section 3 and section 4. And then we'll get something that looks like this. That's the graph of the derivative function. Now there's only one more thing that we need to consider, and that's the endpoints of each of our segments of the graph of the derivative function. In other words, should we graph endpoints that look like this, or should we graph endpoints that look like this? And the answer is that at the end of each of our segments that represent the slopes of our lines, we should have open endpoints. And here's why. For example, let's look at the point when x equals -5. So this point here. Do we know the slope when x is equal to -5? No, we don't. Because how many points does it take to calculate a slope? It takes 2 points. Well, when x is equal to -5, we only have 1 point. With only 1 point available, we can't definitively say what the slope is at that single point. And that's why we use open points to graph the end points of our slope segments. And we could say the same thing about every one of our endpoints. For example, when x equals 0, at that singular point, do we have enough points to determine the slope when x equals 0? Is it +1 at that point, or is it -1 at that point? Well, because we only have 1 point, we can't perform the slope calculation when x equals 0, and so therefore we use open circles. Let's do one more example. In this example, we're given the graph of the function and we're asked to sketch the graph of f prime, the derivative. The graph of our original function is made up of 2 line segments. One from when x equals -1 to when x equals 2. and the other from when x equals 2 to x equals 6. The segment from when x equals -1 to x equals 2 has a slope of 2. And the segment from when x equals 2 to x equals 6 has a slope of -1. Now let's graph these two slopes on our graph on the right. On the interval from x equals -1 to x equals 2, the graph of our function will have a height of 2 because the original function has a slope of 2 on that interval. And then on the interval from x equals 2 to x equals 6, our graph will have a height of -1 because the slope of our original function is -1 on the interval from 2 to 6. And there's the final graph of f prime.